I think we can maybe start. People start coming in, but if you want to start on your slides, Joshua, I think now works.
Sure. Yeah. Okay. So yeah, thanks everyone for coming. So this tutorial is going to introduce Eelbrain, which is a Python toolbox for analyzing neuroimaging data. And specifically, I'm going to talk about these encoding and decoding models using Eelbrain, right? So why Eelbrain? So I think there are two big reasons. One is if you want to use Python and you're familiar with Python. So I think MTRF Toolbox is really great, but if you're more familiar with Python, maybe Eelbrain could be an option. The other reason is also if you want to use boosting for TRFs. So there is also a MATLAB implementation of boosting, but I think Eelbrain boosting has been very well tested, and it seems to work really well. So as if you came from my talk, boosting is a little different to ridge regression. It has these parser TRFs with the components being a bit easier to see. That doesn't really mean that it's a better TRF, but it may be better if you really want to detect components and try to understand the components for the forward model. Some other reasons are that it's compatible with MNE Python. So this is a library, a toolbox that's used for a lot of MEG and EEG analysis, for visualizing, and especially for source localization. So if you're interested in source localization, especially since coming from an MEG background, that's something that we did quite a lot. So Eelbrain works with this toolbox as well. And then lastly, it's also easy, it's flexible, and it's high level. At least I think it's like that. Maybe you will too after today. So I can't talk about Eelbrain without talking about Christian Brodbeck, who is sort of the brains behind all of it. And I'm sure if you have any further questions, you can reach out to me or even to him and ask any questions about Eelbrain. So just a quick overview of how Eelbrain fits into the Python ecosystem. So Python is this open source ecosystem, and Eelbrain works with a lot of the underlying libraries. So you have NumPy for arrays and mathematical operations, SciPy for signals, Matplotlib for plotting, and then Jupyter, which we are going to use today, is for notebooks. So all of this interfaces with Eelbrain, and also you have MNE for the EEG and MEG pre-processing of loading files. So Eelbrain is going to use MNE to do all of that. And then once you actually use Eelbrain for this encoding or decoding analysis, you can also export that into more statistical software packages to do some statistics on it if you want. Eelbrain does also have statistics that you can do, and I'm going to go into that as well. Okay, so let me now stop with the slides and go into the tutorial. So I'm going to stop sharing for a bit. So as a quick question, did everyone get Eelbrain installed? Were there any problems with installing Eelbrain? Maybe you could raise a hand if you had problems. Can maybe some people could just raise a hand if they have installed Eelbrain already? Yep. Looks like there are a few hands up. Yep, good. Okay.
Great.
Great. Let me just get the screen sharing. Yeah, great. Yeah, and also another, just for me to get an idea of the audience, like how many of you have used Eelbrain before? Can I see like any hands for that as well? Okay, a few, one or two. Okay, and how many of you have used like Python before?
Or maybe how many people have not used Python?
Yeah, so it seems like a lot of people have not used Python, right? So I see like
it's sort of a mix.
Hands. Yeah. Okay, sure. So, right. So let's go back to my screen. You can see my screen, right? The tutorial.
Yes, I can see your screen.
Okay, great. Okay, so please, if you have any questions, so this tutorial is going to introduce Eelbrain and not specifically Python. So that would be a bit too much to do in 2 hours. But so if you have any questions with Python on exactly what's happening, just stop me and ask me about that as well. Okay, so
actually, I want to make a couple of comments. So if you're new to
ahead.
Python, Jupyter notebooks are super. You can actually run through each of them if you haven't tried to do that already. It's a good way of learning Python as well, just working with these Jupyter notebooks. So that's what Joshua has up. And the other thing is, if anybody has questions, you don't have to raise your hand. I would recommend just turning off your mic and chiming in and asking the question. That's all good. So cool.
Yeah. So just be as interactive as you want to, and stop me anytime if you have any questions or problems. Okay, so just so I'm assuming that all of you are able to get this page, the CNSP tutorial notebook. So the first part of this is just some introduction to the tutorial and what data sets we are going to be using. But I'm going to skip that and just move on. So the way I'm going to do this tutorial is to just move through each of these cell blocks. And the way you can run these is Shift-Enter. So if you just press Shift-Enter here, this is going to basically import all the necessary libraries. So the way Python works is you have different libraries that use different, or packages rather, that use different functions, that are used for different functions, right? So these are pretty generic libraries, and then these are specific to the EEG or MEG data processing. So you have MNE, and then you have Eelbrain, and I'm importing it with this sort of variable here, the eel name here. So everywhere that you see eel, that's going to be an Eelbrain function. And then TRF tools is another part of Eelbrain actually. Right. So and then you should have your folder set up like this. So you have the data and the results, and then you have this tutorial notebook. Okay, so moving to the first section. Let me just make sure that, okay, if anyone has any problems at any point, once again, just stop me or just raise a hand at least so that I can know and we can go through it. Right, so the first part is going to be about loading some data and visualizing it and looking at TRFs. So this is sort of a very quick overview of what Eelbrain can do. I'm not going to go into the details of what each of these methods are. That I'll do a bit later on, right? So not in the first section. So in this section, we are going to load some pre-processed EEG that's already there inside your data folder. And it's saved as a pickle file, which is a Python, a very commonly used data format for Python. So you can load it using this Eelbrain function, eel.loaded_unpickle. And then we also have some predictors. In this case, they are speech envelopes. So if I load them and then just print what they are, you can see that the EEGs are this ND variable, and they have 4 cases, 124 sensors, and so many time samples. So the cases in this particular data set is trials. So it's just a way of calling the trials. So there are 4 trials with 124 sensors and this many time samples. So this is actually from a pre-processed data from the Leyland speech data set. So for now, just run this. And then if you want to take a look at the data, you can run this. So we are first going to plot the predictor. So I'm just plotting the first trial of this predictor. And you can see that here. So this is the speech envelope. And then we're also going to plot the EEG. So I'm again plotting the first trial of the EEG. And you can see that over here, the way it's been plotted is you have a time axis here in seconds, and you have sensors over here. And you can give it certain time points that you're interested in. And so in this case, I just randomly selected 3 time points, and it will show you the topographies at those time points. So I will go into all of these functions and exactly how you can use them and all of that a bit later. But does everyone is everyone able to run this? Is it working fine for everyone? And it's fine if you do not understand all the details, it's fine, because it's not, this part is not for the details. Okay, I'm assuming it's fine. And so now we can actually compute the TRF. So since we have our pre-processed data and our predictors, we're going to use this boosting function. The first argument is the response. The second is the predictor. We are starting the TRF at 0, and we are going up to 300 milliseconds. So all the time is going to be in seconds. So it's 0.3. And this is basically the smoothing of the TRF. So basically it's what's the width of the basis elements we are using. If you remember in my talk, there are these shapes that we use. So it's basically a Hamming window basis. So it's going to be 80 millisecond width Hamming window, and this is for the cross validation. I'm just using 2 partitions. And if you run that, it should, it's pretty fast because it's only 4 trials. So now the TRF has been saved inside this res object. Oops. And if we want to plot the TRF or look at the correlation, we can do that with this code block. So it says the correlation accuracy averaged across sensors is 0.05. And this is what the TRF looks like. So here we are plotting every sensor. So each line is a sensor, and then we are telling it to look at the topography at 150 milliseconds. And then this is the same type of plot that we saw before. It's the same TRF, but plotted with this sensors on the y-axis. And we can see like 3, interesting time points maybe that. Okay, has everyone got this working?
In this case, you're fitting it independently to each channel?
Yeah, that's right. Yes,
yeah.
Boosting will fit the TRF independently at each channel. Yeah, that's right. Yeah, so has everyone got this working? And once again, if you don't, get all the details of the functions, I can tell you later on, but yeah. Okay, I think it's all fine. Right. So again, at any point, just stop me if I'm going too fast or too slow even, and I'll speed up a bit even. Okay. Right. So Eelbrain is very good with representing time series data. So I think this is sort of the main advantage that I find with Eelbrain, at least at the low level, is that you have these data types called ND variables, therefore n-dimensional variables, right? So this EEG that we loaded was an ND variable. So now I'm going to go into sort of the details of what the Eelbrain data type looks like. So you can look at the ND variable by just printing it out. So let me just run this whole block. So the first line is the ND variable, right? You have, as I mentioned before, and then you can look at the trials of it. So you can just subset into it by using or index into it, and that's going to give you just the first trial. Then you can also access the actual data as a NumPy array, and that's just going to be an array of numbers, right? And the way to do that is using this .x property of the ND variable. So if you do that and then you look at that EEG data, you can see that it has a shape that matches the the sensors. And if you just look at that like this, it's just going to be a list of numbers, right? So that's basically that. And then the important thing about these ND variables is not only do they have the data, but they also have dimensions, and these dimensions have interesting or important properties that are saved along with it. So this current data has a sensor dimension and a time dimension, and this sensor dimension will have all the sensor locations and the connectivity, and this time dimension has a sampling frequency and all of that, right? So it's going to make it very easy, at least in Eelbrain, to use these ND variables when you want to plot things or compute things or filter things or anything like that, right? So let's look a little bit into these dimensions. So you have the time dimension is called the uniform time series, or UTS. So basically, if you look at this block here, you can see that EEG.time. So it's just the name of the dimension. That's a property in the object. So if you do EEG.time, you can see that it gives this output, and it says it's a start time of 0, a time step of 0.015, which is 64 hertz sampling frequency. And then this is the number of samples that are in the time series, right? And you can also look at them individually. So for example, if you want the sampling frequency, you can do T step and then 1 over that. So that will give you 64. And then you can look at the time, mean time and the max time, and so on, right? So Eelbrain has a lot of documentation. So if you take a look at the Eelbrain documentation, it's very good. You can still see this window, right? So you can take a look at all the different properties that this UTS object has, and for any of the other questions you have, you can take a look at the documentation for more details. So very quickly, to create a time dimension, you can just eel.uts with a t-start, t-step, and a number of samples, and that will give you a new time dimension. And you can always just look at the actual time points by the uts.time. So that's just going to give you all the time points. So now, interesting point about this time dimension is you can easily subset into them. So if you just do EEG, which is an ND variable with a time dimension, .sub, and then you tell it to subset the time dimension between 1 and 4 seconds. So all the units in Eelbrain are in seconds, or the time units. So this would just give you a new ND variable, but it has less samples because it's only from 1 to 4 seconds, right? So you don't have to worry about sampling frequency and all of that. Okay, same type of deal with the sensor dimension. So here you can look at EEG.sensor, and that's going to tell you it's a sensor dimension with 124 sensors, and the type is a biosemi sensor type. And then you can look at the names by sensor.names, and so you have all the sensors here. And you can also subset into that by just EEG.sub sensor equals whatever sensors you are interested in. And if you do that, you get a new ND variable with only those sensors. Okay. Then we can create our own ND variables. So all you need to do is this line over here. So everything before that is sort of setting it up. But basically, if you just do .nd variable and then you give it a data array, for now I'm just giving some random array, and then you can give it a sensor dimension and a time dimension, which I've defined up here. And you can also give it this case dimension. The case dimension is like a placeholder for trials or for subjects or for tasks or whatever you want that is not, it's just a placeholder dimension that you can use. So that's basically going to give you a new ND variable with, like, say 10 trials and then 124 sensors and this many time points according to our dimensions.
Could I also import data from M&E Python with the function?
Yes, exactly. Yes, you can. It's very easy to import data. So if you have M&E objects like FIF objects or raw data or anything like that, it's just a one-line command to import things into this ND variable format. Yeah, okay, I'm great. Sort of going to the low-level thing first, and then I'll talk about importing data as well. Yeah. Yeah. So then the thing with ND variables is you have all these operations on ND variables that you can do. So these are like typical operations you may want to do, and you can also do it on a particular a particular dimension. So for example, mean over sensors, or RMS over sensors, and so on. You can change these operations as well. Maybe you want the RMS over the sensors and the mean over the time or something, and the max over all the trials, something like that, right? So you can do all of that, and that will just, I mean, there's no output. There's no output for this particular block, but yeah, it's just to show you that these are things you can do. So if you want even more operations and everything you want to know, you can just look at the documentation. There are quite a few that are useful for EEG, MEG, data analysis. And I think these are all just sort of high-level functions or methods that make it easy to work with them. You don't have to keep, writing out lines of code for each of these. Okay, and then plotting ND variables. So here there are several types of plots you can do with Eelbrain. So the simplest one is the uniform time series plot. So that's just what you would plot for one-dimensional time series. So in this case, I'm taking the RMS over sensors, and I'm just taking from 0 to 4 seconds, and I'm plotting that. So that's going to, that's going to give you the first plot here. So this is the EEG RMS over sensors, and then you just to let you know, like, you could also smooth things directly. So in this case, I'm smoothing it before plotting. So this is going to smooth it with a 500 millisecond Gaussian window. You can give it different parameters, the smoothing function, I think. So you can give different, window widths and so on. And that's just going to give you a smooth EEG. You can also do frequency domain things like the FFT or the power spectral density. And you can plot those as well using UTS. So that's what you see over here. like you can do, you can see, of course, the FFT, and then the power spectral density according to Welch is Welch method is much smoother, of course. Right, and then more interesting, I think, is this plotting of the sensors. So this is where the information of the sensor location that's stored in the sensor dimension is automatically taken into account by Eelbrain. So you can do plot.topomap, and let's say at a particular time point, you want to look at the topography. So you can do that, and you should get a topography here. If you want to plot it as a butterfly plot, so you can use this topo butterfly, and here you have basically the butterfly plot with across different sensors, and then you can give it a time point that you want to see the topography for. And then the last one is plot.topo array. So that's going to be like this, I think, the one that we showed before, where you have different time points that you're interested in. So you have the topographies down there. So you can give those time points in here when you plot them. Okay,
so if you change set time in that thing, it'll just change what time point is being in the topography. Yeah,
sorry,
cool.
Just 1 to 3, right? So yeah, so let's do 2.5 or something. So all of this is actually so now it's at 2.5, right? You can see this line here. So all of this is actually interactive when you run it in a like a terminal or a prompt. You can actually move your cursor and you will see this updating. At the moment, it's not there for Jupyter notebooks. So if you really want to see some interactive plots, you can run Eelbrain in a terminal, and you can sort of move your cursor and zoom in and zoom out and all of that sort of thing as well. Maybe I showed that towards right at the end of the tutorial. Yeah, and if anyone here is interested in doing source localization, you can have the same types of plots for brains as well. For different source localized data, you have a butterfly plot with the brain showing up here at a particular time point. So this is going to be based on MNE, the plotting functions in MNE a lot. And yeah, so that's the basic concept for the low level, the data structure. I think that's really important to get a handle on what is going to happen in the next few steps. Any questions so far?
Has anybody run into any issues when you're running these? Okay.
Okay. Am I going too slow? Is this like too easy for people, because it's pretty low level?
I muted myself and then started talking. So actually, there's a question in the chat. Can we do an average topo plot over all time points of a series?
Yeah, you can. So you would do it like this. So let me just do that. So you can do eel.plot.topo array. And then let's say you want the first, trial, and you want to average over time, right? So that's all you need to do. And then, yeah, that's it. Oops, what happened there? Oh, sorry, not topo array, it's topo map, because topo array needs the time dimension. There you go. Yeah, so that's, the average topo map of all time points. I don't know whether it really means anything though, but, you can do it. Yeah. Okay, any other questions?
So
these methods on the ND variables are very powerful. Like you can use them very easily when you want to plot things or anything. Okay, so now we can go into the next section, which is about pre-processing. So now let's look at how we can load some files. So first, let's just start with the wave files, because we usually work with audio, but you can of course work with other types of files as well. So Eelbrain has this load.wave. It will directly load a wave file, and we are just going to select one of the channels, left or right, and just selecting one of them. So if you take a look at that, wave file has been loaded as an ND variable. It has so many time samples, and then we can extract the Hilbert envelope using this function here. This would extract the Hilbert envelope. So that's also going to be an ND variable, right? So that's something that maybe you want to do when you want to do like envelope TRX. To do some resampling or filtering, there are some Eelbrain functions. So this is an Eelbrain function, eel.resample, and you pass it an ND variable and you tell it the sampling frequency. You can use filter data for filtering. This is the low pass and the high pass, and there are many other parameters for what type of filter. If you don't give it any parameters, it's just going to do an FIR filter. And then and so we are just going to filter, resample it to like 100, and this would also clip it, like anything that goes below 0, it would clip it, right? I'm also just giving it a name. So each ND variable also has a name, so that's just going to make it easier to see on the plots, so that you know what the name of each ND variable is. So that's that. And this is one way.
Can we also get the transfer function of the filter that is applied?
Yes, you can. I'm not sure if you can with Eelbrain, but you can do it with MNE. So Eelbrain works with MNE. So I think it's like, what is it? MNE create filter. So that would give you something.
Okay, so the eel filter functions are basically a wrapper for the MNE
exactly
filtering. Okay.
Yes, gotcha. It's exactly, yeah. So if you are familiar with MNE, it's like exactly the same. It's just calling MNE's filtering and MNE's resampling under the hood. Yeah, most of the signal processing is based on MNE. The things that are specific to TRFs are what's new in Eelbrain, I think. Although there are some types of TRFs in MNE as well, but not boosting at least. Okay, and then this is just normalizing. So for normalizing, I'm just, so this is the actual data array. So if you want to do some low level manipulation on the actual data array, you can always do that by just .x. And then, I'm dividing by the max. So, you can change this to the standard deviation if you want instead of the max, whatever. Yeah, and so that's going to give you, I don't plot it immediately. I plot it a bit lower, but we can plot it just to take a look at it. So, oops. So you can do like eel dot. Yeah, so that's what it looks like, right? So that's a WAV file, and that's the envelope that's been sort of smoothed. So some of these high peaks are smoothed down now. Okay. So yeah, and for plotting, this double list here is so that it plots within one subplot. If you give it to a single list, it will plot it as 2 subplots. That's just the way that Eelbrain plotting works. Okay. Then another thing you can do with Eelbrain, and this is in the TRF tools package, is using this gamma tone filter bank. So that's something that we have been using a bit. It's just a way of extracting the spectrogram. So here you can run this on your WAV file. It'll extract the spectrogram. It may take a few seconds to do that. And basically you get this sort of spectrogram as the output. There are other ways to extract a spectrogram. It's just that this may be more relevant for auditory models, but yeah. So let's let that complete. And yeah, so now I'm just plotting the spectrogram using plot.array. So there's another plotting function. It's not a topo array, it's just an array. So it has 2 dimensions, and Eelbrain knows that it's a frequency dimension here and the time dimension here, because it's even this spectrogram is an ND variable with those 2 dimensions. Yes, then we can average across this spectrogram to get the envelope. So just to collapse it across the frequencies to get a very, the power envelope. So here you collapse it across frequencies. And then again, we are doing some filtering and resampling like we did before. I'm just doing it in one line here. And then some, normalizing again. I think I did standard deviation before, so I can just do standard deviation again. And if you plot, plot them together, you can see all of them. I think before it was, normalizing by the maximum, so that's why the previous plot looked a bit different, but this plot's normalized by the standard deviation. So, but yeah, so you see the three things that we have computed here. Okay, so that's just about envelopes and stimulus. There is also an easy way to load CSV files that maybe you have your phonemes or your surprisal values, or some sort of other type of coding for some impulse predictors. There are some easy ways you can load it into Eelbrain as well. I don't have it here right now, but you can sort of make an impulse predictor ND variable. Okay, if you just know how, give it like the time points of where the impulses are and the values. Right. Any questions so far? Is everyone up to this point? Like, has everyone got things working? Yeah, I think
Aaron
so.
gave a thumbs up.
Yeah, I'm assuming that he speaks for the group. So yeah. Okay.
I speak for myself.
Okay. Right. So, okay, so we can just move on to the next one, which is maybe the the most important, which is how do you load your EEG or your MEG files, right? So the easiest way to do it is using MNE. So if you, from a raw object, so if you have like a raw BDF file or CDF or some other, for MEG file, MNE has a load of files that it can support. So if you just look at all the different types of files it supports, all these files, right? So it can basically load all of those. And as soon as you load it into this MNE, it makes it into a common data structure, and then you can directly load that into Eelbrain as well. So once you load it, so it's just a two-step process. You just load it with MNE, and then it will load it into Eelbrain and convert it into ND variables with the appropriate, sensor dimension, time dimension, all of that. So I'm not going to go into that in this tutorial, but there is a script that's available. So Eelbrain actually has a tutorial paper with the corresponding GitHub. And in that GitHub repository, you have like scripts that load it from MNE. So you can take a look at that on how you can do it. You can sort of load events or epochs, or evoked responses, or even the raw response into Eelbrain. Some other ways you can load files, you can load it using Python's pickle format. You can load MATLAB files using some of Python's MATLAB loading methods. But I think what we are going to do today is loading CND files. So CND files, I think you all know about it since we've been talking about it in this workshop. So the way you load this CND files, let's see, there's something in chat. Can you load in yes, you can. So I think the way you could load in, you could save your file as MATLAB files and then load it in your pre-processed data. You could load it in using this MATLAB functions to load it in. I think there's also a way to load in like EEG-Lab.
Yeah,
like there's something here, this thing. I have never worked with EEG-Lab, so I don't really know all the details, but I'm sure it's easy. Yeah. So this thing may probably, you just have to give it the, is it .set file that you have? Okay, yeah, I'm assuming that this is how you would do it.
Heather, did that answer your question? I heard you saying something.
Yeah, I was actually more wondering, so I guess I should just look through step 3. I was wondering if there are any functions that are applied that wouldn't be applied by pre-processing more generally, like something that gets it formatted and ready to run through the Eelbrain toolbox for estimating the TRF.
Okay. Yeah. So
maybe I'll hold my question for a minute and come back if I still have it.
Sure. Yeah.
Thank you.
I think here I'm going to go through all the steps you would typically do in like a simple pre-processing pipeline. But yeah, you can fast forward if you already have the preprocessed data at any stage. But yeah, so here for loading the CND files, you should have your data set up in this structure. This is the same structure that we've been using, right? You have your tutorial folder, and then you have the Eelbrain tutorial folder, and this is the file. And then you have your data set and Layla speech. So as long as you have this in here, this should work. It's just going to load one subject, and you can do that by load.cnd. So this is an Eelbrain function. So you just do load.cnd, give it the path, and that's going to load it. And it's going to load it into another Eelbrain object. It's a dataset object. You can take a look at the documentation more about that. I'm not going to go into it in detail, but it basically is a way to store data with columns and rows. So you have, you can just look at the first few rows using this .head. So you see it as an EG column, a trial position column, and an extra channels column. And this extra channel is actually the mastoids. And you can look at, let's say, the first element. It's going to be an EEG with a sensor dimension and a time dimension. And if you look at the first element of the external channels, it's it has two mastoid channels. So once you have that, we are just going to combine all of this into an EEG, into an ND variable with 20 trials. So there are 20 trials in this EEG data set. So this is just going to make, I'm also just switching the time and sensor dimension, and I'm also doing this in a more, in a way that shows you can make a new ND variable, and you can crop the first, like you can crop some time if you want to, or you can even pad the time if you want to align it with the stimulus and so on. But yeah, but once you run this, so just to, maybe I should just tell you, just to be clear, so here we have this EEGs initialized as a list, which we are appending to in each trial. And then this combine function in Eelbrain is going to take in a list, and it's going to combine it together with a case dimension. So that's all that this combine is doing. So it's just going to make it into one ND variable with a case dimension, and that's just going to make it easier later on when you want to use them for plotting or for running TRFs or for anything else. Okay, I'm doing the same for the extra channels. It's exactly the same code. So in this case, you have 20 trials, 2 channels, and some time dimensions. And then just to show you how you can load some MATLAB files, there are like better ways to do this, but this is one of the lower level ways, I think. So you can use SciPy, which is a Python package or library, to load it. And MATLAB files, when you load it into Python, it may look a bit weird if they have structures. So there may be like several indices. You can always just look at what the file looks like and go into those indices and then extract what you want. So in this case, it just happened that you had to go through those indices to get into the actual data. And so if you look at it, you can see that it has 2 features. So basically, I'm just looking at the shape. It has 2 features and 20 trials. So this is the stimulus from the Layla speech. You can, of course, directly load it using load.cnd, since this is in CND format. So you don't have to go through this if your math file is in CND format. You can just do load.cnd, and then you have, again, another data set where you have your envelope, speech envelopes, word onsets, and then some more information about them. Okay, so is that all fine? Yeah, and just one more thing here. I'm just going to store the envelopes in a list of NDVARs, just the same way that we did before. Right, so is that all fine? Everything good so far? Okay, I see a few thumbs up, so I'm assuming everything's good. Right, so now to filtering and downsampling. We did this before for the envelope as well. Like I said, if you don't give it any parameters, MNE, it's an MNE filtering setup, so it's just going to use the FIR filters. So in this case, we want to, let's say, 1 to 8 hertz, do a bandpass between 1 to 8 hertz. So I'm just filtering the envelopes, and then I'm resampling them to our sampling. I think this was defined as 64 hertz at the top or somewhere. And I'm just doing the same for the EEG and the mastoids. And so if I run this, it may just take a few seconds to do all of that. And now you can see that these three, which I'm printing out, they have 20 trials and the same amount of time samples at the same sampling frequency, right? Okay, and then you can also reject bad channels. So in this case, we are rejecting bad channels. If you want to interpolate bad channels, there are some M&E functions to do that, which you can easily do with this as well. So in this case, the way I'm going to reject bad channels is look at the neighboring channels and seeing the correlation. So this function neighbor correlation is just going to take in an ND variable with a sensor dimension, and it's going to give out an ND variable with the correlations in that sensor dimension. Yeah, and this is just concatenating it across the time dimension. If you give it, so it's just going to concatenate these cases together. I think you may not even need to do this, but yeah. So if you run this, it will tell you that, let's say, you know, a threshold of 0.3 is good enough. So if it will tell you that there are 4 channels that are below that. So these 4 channels are, you know, the bad channels. And the way to reject it is just get the list of names that you want to reject. So in this case, every channel that's above 0.3. And then in your EEG, we just sub into the sensor dimension using only those good channels. So now this new one has only the good channels. And then you can subtract the mastoids by just first averaging across the channels and then subtracting. So this is to reference it or re-reference it. And then you have some sort of normalization, maybe with the standard deviation. So this is going to just give the standard deviation across all channels, all time points, everything. Okay, is everything good so far? So this is just one possible pipeline. Of course, you can, you know, you have flexibility to do it the way that you want. Okay, if there aren't any questions, then moving on.
I guess I have a question. So you
Yes,
use
go ahead.
neighbor correlation here, but are there other ways of identifying bad channels, like with spline?
I actually haven't looked into it. I mean, M&E may have. I haven't looked into other methods actually.
Okay.
Yeah. Usually what I do is either neighbor correlation or some sort of thresholding to detect flat channels or something like that. But yeah, I haven't done anything else. Yeah.
Okay, cool.
Okay. Right, and then just to let you know that you can do ICA. So this is not Eelbrain, this is actually MNE. So MNE does ICA as well. So you can apply the ICA. So this is one way in which you can convert an Eelbrain in. Yeah.
Sorry, Joshua, just a quick question about the last part.
Yes.
So Talat asks, do you interpolate bad channels?
No, so here I'm just rejecting them. So you'll see that there's only 124. So I'm rejecting the 4 channels. But you can interpolate them. It's just that I think you need to do it in MNE. So it's there in this, where is this Alice dataset script? Yeah, so when in this script where you load it from the MNE, then you can also interpolate it using the MNE objects and then load it into Eelbrain. So some of the more sort of, you know, low-level things are not all implemented in Eelbrain. So you can just do it in MNE and then take the data into Eelbrain. Okay. Right. So now, yes, so we are in artifact rejection using ICA. So here we are going to just make an MNE object from the Eelbrain object. So for people who are familiar with MNE, just in a way that you can, oh, there's something in the chat. I think someone has a package that is good with MNE. So yeah, take a look. So now interpolating, sorry, so there's another one, interpolating channels. Do you mean that, I'm not sure exactly what you mean by affect implementing the TRF functions.
Oh, so like if you leave out channels, can you, does it affect how the TRF is shaped?
Oh, okay. Yeah, of course. I mean, if you have bad channels or leave out channels, then you don't have that TRF. But you shouldn't be rejecting like, half your channels or interpolating half your channels. So I don't think if you just interpolate 4 out of 124, I don't think it's going to be an issue. As to the question of mismatching dimensions, it shouldn't have any errors because you're going to do your TRF on this data set and it only has these sensors. So it knows that, you have a subset of the sensors. So it's not going to give you any mismatch dimensions. Is that what you asked? Okay, yeah, great. Right, so to do ICA, yeah, so I was talking about changing the Eelbrain ND variable onto the MNE object. So the MNE objects have this info property that has all of this information on sensors and so on. So you can do that. You can do mne.createInfo, and you can give it the channel names. So this is just the concatenated data. So I'm just giving it the channel names, the sampling frequency, and the type of channel. And I'm telling it that I'm using this this particular montage, electrode montage. So this is all MNE. And I'm also creating a new array using this data in MNE and passing this info object. So this is a way in which you can quickly convert an Eelbrain or any sort of matrix into an MNE object. Right, so these montages are like the default that's already there in the MNE package. So as long as you're not using some really completely custom montage, you should be able to just give it the string and do it. Right, and then we want to do it because ICA is done using MNE. So you can do mne.preprocessing.ica, and that's going to give you an ICA estimator or ICA object, and that's going to and then you fit it on your MNE object, which is this raw data, let's say, right? And yeah, so that this may take some time, so I'm not going to run it here. If you can run it. Otherwise, you can just load the ICA that's already been pre-computed. So like it's saved using ICA.save, and you can load it using an MNE function again to load it, right? And then I'm not going to go too much into all of this, but just to show you, you can plot these components. I mean, you can do that in MNE as well, but you can do it with Eelbrain as well. So one thing that's really useful with Eelbrain is it has this interactive ICA plotting window, which if you run it in the terminal, it will show up, and you are able to like reject components and look at the time course and all of that interactively. So maybe if we have time at the end, I'll show you how you can do that. But if you want to keep it in Jupyter notebooks, you can just do it manually. You can look at like the first 10 components, the topographies, and then you can look at the time courses of these first 10 components. Obviously, this one is probably some eye blinks or something like that. And this also seems to be a bad component, and that agrees with the topographies component 1, component 9. So, you could exclude those. And then we want to apply it. So again, we need to convert it to some MNE and apply it. So I'm not spending too much time on this since I think ICA is something that many people would do with their own, method of ICA, either EEG-Lab or MNE or whatever. It's not specific to Eelbrain, but I'm just showing you that it can be done. And yeah, and so this is before ICA. There was this eye blink. It's been removed after ICA. It's not surprising. Okay, so any questions on the pre-processing so far? All good?
Hi, Joshua.
Yes.
I actually wanted to clarify my question about
Yes.
the bad channels and the mismatching dimensions or error. So far, whatever the pre-processing you have been talking about, it's about one trial, right?
No, it has like several trials. Do you mean the, oh, okay. So you mean each trial has a different number of sensors?
Exactly. So what I'm talking about, like if each trial has a different number of rejected channels, how are you gonna implement it in TRF? You know what I mean?
Sure. So
Yeah.
I have not directly worked on that. I'm not sure if it actually gives an error. Worst case scenario, you can, sorry, yeah.
Yeah, so if I mean, I have so far implemented in MATLAB, so I'm not the best person to talk about Eelbrain or like,
Sure.
you know, the Python thing, but apart from the language, what we use or not, whether it's MATLAB or Python, what my understanding is for like a very simple situation when you have like 10 trials, where you have like 9 training trials and 1 testing trials. So if those 9 training trials does not have the equal number of sensors, like one probably have like 124, one have 120 or something like that. Like my question was more about like, if you have those different number of sensors, does it give any error while you are implementing the MTRF train, MTRF crossval, or whatever the Eelbrain, you know, functions?
Yeah, I think at the moment Eelbrain, yeah, it will give errors because you would have a different type of split then for each.
Exactly.
It doesn't have a way to handle that missing data. But for your case, like you can always just do it independently. You can just run the TRF independently at each channel, because that's what's happening under the hood. It doesn't really matter. It doesn't care about other channels. So you can just run a TRF in a loop outside for each channel, and then you only have the channels for each trial, right? So yeah, or you can interpolate bad channels, like someone just mentioned, of course.
Yeah. So that was more of my question, because like what I have experienced, I don't remember the details. Like if you do not interpolate the bad channels and you don't have the exact same number of channels, some error of mismatching dimensions might occur.
Yeah. I think that happens in Eelbrain as well. Yeah, because it just does the same type of splits for all of that. Yeah.
Okay. All right. Thank you. I just wanted to clarify the questions. Thank you.
Sure. Yeah. Here, yeah, we did concatenate across trials, but even when you concatenate across trials, it's going to throw an error if you have some trials with more sensors. Actually, you can't make an ND variable with differing numbers of sensors for each trial. So yeah, so someone asked about that. Yeah, so you would have to have the same number of sensors for each trial if you want to make it into one ND variable, but you can always run each sensor separately in a different ND variable. Then you don't care about mismatching trials. Okay, right.
Actually, Joshua, I have kind of a newbie question, because I mostly work with MATLAB, a little Python. So if you set up like a pre-processing pipeline in a Jupyter notebook, is it possible to sort of turn it into something that's executable so that you rerun the same pre-processing pipeline without having to go cell by cell?
Yeah. So there is a way to convert Jupyter notebooks to Python files. So you can just convert it using I forgot what the name of the actual package was, but it just basically would convert all of that into a Python file, and then you can just run that Python file.
Okay.
I'll just look that up and send it to you if you need. But yeah, if you just Google it, you should be able to find it. Yeah.
Okay. Thanks.
Yeah, it's just another package you need to install. Yeah. Okay, so now we can actually go to fitting some TRFs. Yeah, any other questions for now? Alternatively, we would concatenate before the bad channel rejection. Yeah, okay, I see. So it depends on how you want to approach it, I think. Do you want to reject the channel across all your data just because one trial it was bad? So, I mean, it's up to you. I don't know whether there is an exact answer on that. Okay, so next, we can go into looking at TRFs. So now we are going to use boosting. So this is just going to fit a TRF for this response based on these predictors, giving it a start time, a stop time, and this is basically the width of the Hamming window You can actually change the window shape as well if you want. There's another parameter to do that. So here we're using a 30 millisecond width. And then this is going to tell it to actually do a separate test data set on which to estimate the prediction accuracy. And this is a number of partitions that it's going to use for the cross-validation. So if you give this, if you run this command, it may take a few seconds to run, or a few minutes even. If you find that it's taking too long, you can uncomment this and load a pre-computed TRF. But while that's running, I'm just going to talk about the cross-validation that boosting uses. So here, if you look at this plot here, this is a cross-validation that we are going to be using. And it may look a bit complicated. So let's, I don't know, if you, so you can look at how this cross-validation would work. Let's say there are 4 trials, and we want, so there are 4 trials and we want 4 splits, and we also want a test data set, right? So what it does is it splits the data into 4 based on your trials. So since we have 4 trials, it's just going to split it on the trial edges. And then it's going to have a training data, which is going to be everything except for 1 validation and 1 test. And then it's going to permute your training data for each of these validation. And then it's going to also do that for all the test data as well. So when you do this, you are basically using all your data to fit TRFs. But the TRF that's estimated on this data set is going to give a prediction accuracy on, sorry, the TRF that estimated on this data set is going to give a prediction accuracy on this test. And the TRF on this split is going to give a prediction accuracy on this test split, and so on. So you're always going to have a prediction accuracy that's going to be calculated on data that the TRF has not seen. And then the final result you get is just the average across all of those TRFs, across all these splits. If you have more cases in your data set, then what Eelbrain does is it still does 4 splits, but it divides that up across the data set so that you don't have all your test data in one part of the trial, or rather one part of the experiment. So it sort of divides up the test data, but you still have that proportion of 1 test to 1 validation to 2 training. Yeah, so in this case we had 20 trials, and since we put our partition as 4, this is the method that's going to use to do the cross-validation.
Is it also possible to return the accuracies not averaged, but for every split?
Yeah, yes, you can. I think you just have to do what is it? Partition results. Yeah, partition results is true. And then that would return the accuracies for every split and the TRFs for every split as well, and all of that. So okay, this is going to return the result object. It's called a boosting result object in Eelbrain. So this object has several parameters and several methods and all of that. So you should definitely go and take a look at the documentation. So I'll just show you how it looks. Boosting result. Yep. Yeah, so it has all these different parameters that you can get into. This partition results is what you're going to get. If you set that to true, then you would have all the results from each partition. But we don't need to look at all of it for this tutorial. So at the moment, I just want you to try to do a quick exercise. So there are 2 interesting parts of this boosting result object. One is the model fit. That's just this result.r. And the other one is the TRF, and that's going to be .h from kernel, from filter. That's why it's called h. But yeah, so can you just try to plot these 2, or just look at them and plot them and just play around with them, and let me know if you have any issues. And if someone has finished and wants to move on, maybe you could just raise your hand so that, once quite a few of you have your hand raised up, then I can just move on to the next one. You should be able to use some of the plotting functions that we used at the top.
I have a question. Is there a way to visualize like the size of the res1.r quickly? So in MATLAB, you can just check what the dimensions.
Yeah, you just have to do this. Just
Cool.
type it out. It will show you what it is. By the way, Jupyter Lab now has a sort of a variable explorer using this debugger as well. So if you want to take a look at all the variables in your workspace, you can do it. I think this is still a little bit, in work in progress. So it may not be as quick, but you can see all the variables you have and what type of variables as well here. That's just this debugger here. So to see the color bar, you can do this. Where is it? I think I had it. Yeah, so if you are plotting something like this, you can have this thing. Yeah, so that should plot the color bar. Yep. Okay, so how is everyone doing? Has everyone done the first part?
I am working on it and almost there.
Sure. Yeah, okay.
Cool. So I have a quick question for myself, I suppose. So when I tried to plot the correlations, it plotted two different
Yes.
plots using the UTS function, and I guess I'm still not sure why. Just even looking at the NDVAR, why there were two plots.
Yeah, it's just a notebook thing. So the notebook cell will always show you what was last typed in the cell as well. So if you just do something like this, or let me go back up to where I plot this one, let's say. Yeah, this one. So if you just do this, it's going to plot it twice because it's going to plot it once, and then the notebook is actually going to give you the result that was generated as well. So it's the same thing. You can suppress it by semicolon, or if you give it a return object, either of these would suppress it.
Okay, thanks. Anybody else have questions?
Is everyone okay? Still working on it? If anyone wants me to move on, just raise your hand and I'll wait till a few of you have your hands raised before moving on.
Anybody else have questions about setting this up?
Okay, is anyone stuck with anything? Any errors?
I'm wondering if maybe we can move on because there's a few
Yeah,
more
sure.
exercises coming up.
Yes,
and then
yes,
maybe we
okay.
can go back and address all of these.
Yeah. Okay, sure. Yeah, so I'll just show you how you can do this. So as I showed on this cell, the correlation is going to be a value at each sensor. So we could use a topomap to plot that. So just plot the topomap and then plot the color bar. If you also want to look at, the average correlation, you can do .mean, and then this is just to format it in a way that is easy to read. And then you can also look at the maximum. And if you want to know what sensor the maximum was at, you can do argmax if you are interested in maximum. Not that it really makes too much sense, but yeah, okay. So this is what it says. It says, the average correlation was 0.06 and the maximum was 0.12 at this sensor. It's probably this one over here. Right. And to plot the TRFs, we could just, so the TRFs, if you want to look at what the TRFs are, you can do this one.h. And you see that it's got a sensor dimension and a time dimension. So we can use the topo butterfly or the topo array. So you would do res1.h. If you give it a particular time for the topo butterfly, then it's going to plot that on the right. And you can give a list of times, and that's going to plot that on the bottom for the topo array. This is just the height and width of the plot. So yeah, if you run that, you should get the same thing. Yeah. So this is what the TRF looks like. I think this was like one of the best participants in the Leyland speech dataset. So not surprising that we have a good TRF. Someone asks, okay, show the code for printing. Yeah, so to those who aren't familiar with Python, this is called a format string. So you can just put F in front, and then everything within a curly brace is your variable, and everything outside the curly brace is the string that's going to be printed. And then you can just get the maximum here from your ND variable or your argmax if you want the sensor. Yeah, and this thing is just formatting it to 5 significant digits so that you don't have a list of, well, I suppose I should have done it here as well, but yeah. Yeah. Okay, right. So now,
just to let everybody know, when we're done with this tutorial, we can also put this code with the solutions on the CNSP website, so you can look at it yourself and go into more detail. And yeah.
Yes, I'll do that. And also, you should, if you're interested, you can look at the Eelbrain tutorial paper and the GitHub. So that has a lot of scripts for a full pipeline of processing TRFs. Not just envelopes, but some word TRFs and phoneme TRFs, spectrogram TRFs, all of that. So yeah, so that's also there if you want to later on. Okay, so another exercise. So this section is going to be a bit, yes, the link to the paper. Yeah, let me just get that on the chat then.
There's also a link to it on the CNSP resources page right at the bottom of the table. So you can find that, and for Mike's tutorial actually there.
Yeah, so it's just here as well. Yeah, and also this has the GitHub. Is there a link to the GitHub on this? It should be somewhere. But yeah, if you just yep. So it's just this is the GitHub. And if you look at the analysis, you can go into this file, and it basically has all the details on how you load stuff from MNE and here you have your interpolation and all of that, and then you make predictors and fit your TRFs and all of that. And yeah, so you can take a look at that. Okay, so the next exercise is to fit TRFs to multiple predictors. So in this case, you can do that by, instead of sending one ND variable, you can give it a list of ND variables, and that's going to fit the boosting TRF jointly to both of those together. So you get, in your result, you will get a list of TRFs, each for the predictors, right? And you can also pass it these arguments. Actually, now, if you want to have a different starting time and a different stopping time for each of these predictors, you can actually give a list of start and stop times. So for example, if you're interested in envelopes only till 300 milliseconds, but you're interested in some word type predictors up to, let's say, 800 milliseconds, you can give that separately. So you don't have to fit TRFs for the envelope up to the same amount of time. But yeah, so this, you can just change this. There should be an eel.boosting here, by the way, when you run it, since we are going to call it with that name. So the first part here is to extract the onsets from the speech envelope. So I'd like you to see if you can do that completely in Eelbrain. We have the speech envelopes, and there are some functions where you can extract the onset from the envelope. So try to do that and plot those. And then after that, you can use the envelope and the onsets together to jointly estimate a TRF. You can do that here.
And one question, that the function calling boosting with two predictors, does that do the same as calling the function twice, one for each predictor, or is this something else going on?
No, it doesn't do the same, because when you call it twice, one for each predictor, you're going to basically fit a TRF without considering the other predictor at all each time. But when you call them together, both of these predictors, so basically in that iterative loop, it's going to check which of these which small change to which predictor increases the error, and it's only going to make that change. And then it's going to keep doing that until the error doesn't improve. Whereas, okay. So if you have, so I suppose if you don't have predictors that are correlated, if they're completely not correlated and independent, then they should be the same type of result. But especially when you have sort of correlated predictors, then you would have, this is much better.
Thanks.
So again, let me know if anyone is running into any problems, any issues, any questions. And if anyone has finished this onset extraction step as well, just raise a hand. If you're really stuck, you can take a look at the ND variable operations in the Eelbrain documentation. There may be a few that are useful.
So I think I found the function that I should be using to do this, but I guess I'm a little bit confused how to use it. I keep getting errors when I'm trying to run it. I don't know if anybody else was running into that issue.
Which function are you trying to use?
So I spotted event impulse predictor.
Okay.
But I guess I wasn't sure how it should operate on the envelope itself.
Yeah, I don't think that's exactly what you want. So that would be if you want to make an impulse. So in this case, the onsets are not exactly impulses. They are like just the onsets of the envelope, right? So I'm thinking more of like, maybe I wasn't clear as to exactly what I was, but it's more like the, basically the first derivative of the envelope, right? So just the parts of the envelope that that's increasing.
Gotcha.
So it shouldn't be impulses, but yeah, if you use that function, you have to give it time points and values at each time point, and it will give you an antivar with impulses at that. So that's not what you want here.
I see. So when you're looking for the onsets, you're looking for like the sort of first derivative of the change.
Yeah.
I see.
Yes.
Okay.
Yeah. Maybe that wasn't too clear. Sorry about that. Yeah. Yeah, but I can maybe show you that since for the sake of time. So there is this diff. Sorry.
I said yes.
Okay, yeah. So there is this diff function. It's just the first difference. So it's just going to take the difference, and then you clip it at 0. So we only want the positive differences, right? So it's like the rectified first difference. So that's just going to give you the onsets. And if you want to plot them, so we have our envelopes and our onsets. So we can plot those together. And you can see that, this is the envelope in yellow, and the onsets are only there when it's increasing, right? So of course, this is a very crude way to make onsets. Like I think a lot of people use maybe some sort of auditory models or something like that to get these onsets, but just for a quick and dirty way, this is one way which you can do it. Okay, and so now that you have these onsets and these envelopes, try to use both of them to fit TRFs. So I'll just leave it on this code if anyone wants to just quickly look at it. Yeah, and now you can use both of these to fit the TRF. How's everyone doing? Can I maybe see some hands up if people are still working on it? Better than complete silence.
I am definitely working.
Yeah. Thanks,
but
yeah, sure. Yeah. If anyone wants to go faster, just let me know. Otherwise, I'll just wait a few more minutes here.
so I think I got it. But it's just taking a while to run.
Yeah. So there should be yeah. So it should finish within like 1 or 2 minutes maybe. But if it doesn't, inside this data folder, inside these results, you should have this file, and so you can load that file. It's a pickle file, so use eel.load.unpickle, and that's a pre-computed TRF if you need to.
Maybe let's continue on because I do want you to start talking about stats a bit.
Yep. So now, so this is how you would do it. So you have your EEG and you have your onsets. Let me just get all the Zoom stuff out of the way. Okay. Yeah. So this is your, so you have your envelopes and your onsets, and you're doing the same sort of boosting. So I'm just going to load the pre-computed one. So you can load that, and then it's the same thing to plot it, right? So you can plot the correlation. You can look at the average. You can plot the so the difference here now is you have one correlation because it's a joint model. So you still have only one prediction accuracy, but you have two TRFs. So this H now has two elements. The first one would be this first one, so it's envelopes, and the second one would be onsets. So you can plot it. It says the correlation is 0.063. I think previously it was 0.060 when it's only the envelope, so it's slightly better. And then you can plot the envelopes, and then the onsets are here down here. And there are some shifts that you usually would see with this onsets and envelopes, but they are very similar. And then again, you see both of them here in the other format, topo array plots. Right, so I'm going to move on unless anyone has any questions. Okay, right, okay, so, okay, another exercise. So this section is exercise heavy, I think, but it's just small modifications to the boosting function that you need to do to make it a decoding model. So just go ahead and reconstruct the speech envelope from the EEG using this same function, yield.boosting, but you just have to switch the response and the predictors, and you also have to give it negative time. So the time also has to be swapped. So yeah, because you're now going on the, you're predicting the envelope, right? Sorry, you're predicting the EEG. Sorry, you're predicting the speech envelope. Yeah, there we go, reconstructing the envelope. Is everyone okay with the speed? All okay? Just a few thumbs up for the speed so far. Okay, I see some thumbs up. Okay, that's great.
Yeah, I think that it's going. My computer is slower.
Okay, so again, for the decoders, you can load it. So let's say you have, it's just to understand how the code works, right? But you can load the pre-computer decoder as well. It's in this data results. It's this one, section 4 decoder. So if you want to load it, you can. And then try plotting it. Okay, so for the sake of time, I'm just going to go ahead because it's just a small modification you need to make. So yeah, so in this case, you have your boosting function, but instead of the response being here, the first argument is instead the envelope, and then you have your response. So it's going to use all the channels in the response to predict the envelope. And then the time that you give it is, you're going to start at minus, let's say 500 milliseconds, and you're going to go to like, I don't know, 100 milliseconds or something. It's up to you what range you want to use for your decoder. And then everything else is the same. So yeah, so I'm not going to run this. I'm just going to load the pre-computed one. And now we can, again, it has exactly the same, it's the same object type. So it's exactly the same properties. It has R and H. And so you can use the same type of functions. And it says, so I should probably print out the average decoding accuracy or the reconstruction accuracy. yeah, so you can see it's much higher than the forward model. It's 0.18, which is no surprise. But on the other hand, when you look at the actual weights, they are, much sparser because it's boosting and also because it's decoding. So it doesn't really need to fit. It's using all these channels together. So if there's redundant information, it's not going to like put values for channels with redundant information. In the forward model, it was using boosting independently at each channel. So every channel would get TRFs as long as there's some information. Yeah, so that's so this I think, yeah, people who are familiar with decoders usually never look at the weights because they are not easy to interpret, but the accuracy here is what's important. Okay, all good to move on to the next section on statistical tests. Anyone has any questions? Otherwise, some thumbs up to move on to the next section. Yep, looks good. Okay, right. So that's how you would fit TRFs. And there are ways in which you can make this whole TRF pipeline, the pre-processing pipeline, all of that much more streamlined so that you can do this without, writing each line of code each time. And so I'll go into that a bit at the end. But let's move on to another section, which is going to be about statistical tests. And I think the way that Eelbrain contributes to this whole thing, because there are so many packages doing statistical tests in different languages, but the way that Eelbrain helps out is by having some cluster-based statistics. MNE also has some cluster-based statistics. So if you want to actually test, significant sensors or significance in the TRF, then Eelbrain can do that using permutation tests with clustering. So I think that's where it's the most useful to use Eelbrain, and it just does it on the ND variables directly. So yeah, so for this, we're actually going to switch the data set a bit. So inside your data folder of this tutorial, you should have all these pre-computed TRFs. And so that's what we're going to use because we want to do a statistical test across subjects. So this pre-computed TRFs, there are three types. There's the envelope only TRF, there's the envelope and onset TRF, and then there's the envelope but with a shifted onset. I think this should be shifted instead of shuffled, but it's basically shifted by 30 seconds. So this is sort of a null model for the onset. So we can load all these paths. So these are the subjects. So I'm not going to go into the code. The code here is like mostly Python and a little bit of Eelbrain. So this is just like loading everything. So just run this block. It'll load all of these. And basically you have your model fits, which are the correlations inside this dictionary. So if you just look at this dictionary model fits, there is this envelope key and it has 33 subjects in this case. The case dimension is for subjects, and it has, the correlation for each sensor. And you have 3 of those. And then for the TRFs, model TRFs, you have for the envelope model, you have the envelope TRF, and that has 33 subjects, 61 sensors and 30 time dimensions. And then for the envelope and onset model, you have the envelope TRF and the onset TRF, and the same for the other model, right? So you have another 2 TRFs there. So this first part is the model, and then the next part is the TRF. It's just the way that I've loaded it. So you can, it's just the way I've defined these things. You can load it however you want later on. But yeah. So yeah, so this, just to give a bit of background, this is the ALICE data set. It's people listening to speech. And I can't remember exactly the EEG system they used, but whatever it was, it seems that 61 sensors. Yeah, so has everyone got this loaded? All thumbs up. Everyone has the data following so far. Yeah, good. Okay. Right. So any questions before we move into the tests? Okay, good. Right. So again, the tests could take a little bit of time to run because they are doing permutation tests over different permutations. So like 10,000 permutation or 1,000 permutations. So if it's taking too long, the tests are pre-computed. You can load it by running this cell. But otherwise, so what I'm doing is I'm just going to store all the tests into a dictionary, a Python dictionary. So I'm just using initializing the dictionary, and I'm going to do the first test of just checking if the prediction accuracy of the envelope model is significantly above 0. And the way you do that is with the test ND module of Eelbrain. So this is test ND variable or n-dimensional test. So you can use a t-test, one sample t-test. This is your ND variable. We want to just see if the model is above 0, has a correlation above 0. So we can give it a one-tailed test that's positive tail. And then this is basically you're going to use the TFCE algorithm, which is sort of threshold-free clustering algorithm. You can not use this. You can use like clustering based on the actual t values. So you can just give it like say p min is 0.05, and then it will do clustering based on 0.05 significance. But yeah, so the reason we use clustering, if people aren't familiar, is because when you have data that's correlated and you're running these tests, you can, for one, Bonferroni or like multiple comparisons would be really hard to account for, but then you shouldn't like just use that because your data is anyway correlated. So then you would use these sort of clustering methods when you're doing these tests. So that's a whole other topic. I'm not going to go into the best type of clustering, but the thing that we've been using a lot is this TFCE, which is the advantage is that you don't have a threshold. It automatically enhances clusters, and then you can run this test. So yeah, so if you run this test, you should get a test object that's stored into this field or this key of the dictionary. So if we, so since I'm going to use the preloaded, pre-computed one, so that's there. And right, so now if you take a look at just what this test object is, it says it's another Eelbrain object. And if you just print it out, you can see if your test was significant, if there are any clusters that are significant, and it seems it's definitely the case here. And then depending on what type of object you send in and what type of test you get out, you can also plot it. So in this case, we sent in the correlation. So that's a topography. And so you can use the topomap to plot this test object. And this topomap function knows that it's a test object. So it will only plot, so it will also plot this significant region. So it seems that all these sensors, except for these three, all of this over here is significantly above 0. So that's how you would do like a correlation, like a prediction accuracy test, let's say, using this method. So that, I think that was a lot of information, but any questions?
Yeah, Josh.
Yes.
Does this test strictly against 0, or does it test against the shuffled values?
No, this is just against 0. I have not put in anything about the shuffle model, but we can do that later. That's later on.
All right, thanks.
Yeah, so a bit later on, we are going to do t-test related. So it's just a paired t-test, so you can test against the shuffle model. Yeah. Okay, so is everyone okay with any thumbs up? If everyone's okay. Everyone got this working? Yeah, okay. Yeah, good. Okay. Okay, if anyone wants me to wait a bit or go slower, please let me know. But okay, right. So we can do the same thing for any type of ND variable. So in this case, we can do it for the TRF. So in this case, again, we are going to just check if there is consistent non-zero activity across subjects. So that's something that may be useful for our TRFs. I mean, for the envelope TRF, you would usually expect that to be the case. So it's not a very important test, but it may be useful for like more complex TRF models. So then you want to make sure which parts of the TRF are significant. So again, this time we're going to give in the TRF. So it's for the envelope model, the envelope TRF. And we want to know both positive and negative sides, right? So the sensors can be positive or negative. So that's why we're giving it a tail of 0. It's going to do a two-tail test. It's the same, yeah, using TFCE, and these are the number of samples in the permutation distribution. So if you run that, but I've just loaded it pre-computed, and if you take a look at it, it's going to tell you that it's again, this test object. It's going to tell you the what you call the significance, and this test object also has several properties. So you can just take a look at all the things that you can see within this test object. So if you go down, you can see you can get the p-values, you can get the t-values, you can get the TFCE map, You can get uncorrected p-values. You can get all these types of things that you need to do if you need to see. And you can also get the clusters, that if there are more than one clusters, you can get the types of clusters. So all these things are there inside this object. So just take a look at the documentation. I'm not going to go into every single detail here. But so using this test object, we can again plot it. So in this case, it's going to be a topo butterfly or topo array. Just for it to be a bit easier, I just told it to color it only in black so that you only see black and gray. So the black parts are significantly above 0 or below 0. If you take a look at this time point, these were the sensors that were significant. And then this topo array is the same type of idea, except just viewed a bit differently. Right. Just going to go and show you the same, exactly the same code. The only thing that's changed is that I'm using the envelope and onset model and looking at the onset TRF. Other than that, everything else is the same code. And you see that the result is, the same, like the onset is also significant for a large portion. Okay, so any questions so far? Any thoughts, any comments? Have people been able to run the test and got it working?
I actually have a simple. Oh,
Yeah.
did somebody else have?
No, sorry.
Okay,
You had a question?
I have a simple question. What is V on the y-axis? I guess I didn't understand that in this plot.
Right. Sorry. So this is actually what do you call V is sort of the units, which is voltage, I think. So it's just normalized units. So since our TRF,
it is the
I don't
TRF.
know. Yeah, this is the TRF. Yeah. So this is basically the TRF, but it's just been masked by the significance. Yeah.
Okay.
So it's the average TRF across subjects, since we have several subjects here. Yeah.
Cool.
Yeah. So I don't really look too much into the units here because a lot of times there are a lot of normalizing and things happening. So yeah, so it's just TRF units. Yeah. Okay. Any other questions? Everything good? Okay. Yeah, it should be arbitrary units. That's usually what I put on the plots. Yeah. So, right. So now we can go into an exercise. So here we were just looking at one ND variable and comparing it to 0. But you can, of course, compare two models. So for that, you would use a related t-test. That's also been implemented in Eelbrain. There are other types of tests as well, right? So please take a look at the documentation. There may be a test that fits your needs better. But yeah, so in this one, you just give it two ND variables as the first two parameters, and then the rest are exactly the same types of parameters here. You won't have a tail, but you'll just have the TFC and the samples. Oh, sorry, you will have a tail. Yeah, you can have a tail if you want. Just so the tail means that it will check the first, the first ND variable. So if you give it a tail of 1, it's going to check on the positive side of this minus this. So one tail test of this minus this on the positive side. If you give it tail of 0, it's going to be a two-tail test. Yeah, so just go ahead and try using this to see if the onsets have improved the model fit. So you would compare the onset model to the envelope only model. So try if you can write out the code. So if you remember these were the model fits, right? So you have the envelope model and the envelope plus onset model. So just see if you can test whether these two models have a significant difference, and the onset, adding the onsets has significantly increased prediction accuracy.
Anybody have questions?
Again, if people have finished or want me to move on, then you can just raise your hand or give a thumbs up, and I'll just move on.
I think we can continue.
Yep.
Yeah.
Sure. So yeah, so this is how you would do it. Just like I said, t-test related, you give the first ND variable, which is the onset and envelope R values, and then just the envelope. And then I'm only interested in whether this increases. So I'm just giving it a tail of 1. You could, if you're sort of more agnostic, you would maybe give it a tail of 0 as well. So yeah, so if we want to plot the test result, you can take a look, and it's when you have this related test, it's going to, if you just tell it to plot, it's going to plot the first ND variable average, the second one average, and then the difference, and it's going to show you the significance on the difference. So it seems that, of course, the difference, it's all in the same scale, so the difference is very small compared to the scale of the actual correlations, but it seems that it is significant. And I think I have, yeah, and you can also actually get only the difference by having the test object dot masked difference. So it's a function that gives you the masked difference. So if you want to, sorry, if you want to just look at what that is, it's going to give you just an ND variable with the masked difference, and it says 28% masked. And so then if you plot that, you can see only the mask difference and the scale, and you see the scale is much smaller, of course, since it's a difference. Right, so that's how you would do testing against another model. So this bit of text is just to say about, okay, now let's look at the shuffled onset model. So if you want to just test the actual onset model versus the shuffled onset model, you can do that as well. So I think most of the code is very similar, so I'm not going to actually do much here because basically it's going to ask you to see if there is any significant activity in the shuffled onset TRF. So you can do that using the same type of test we did before. You shouldn't find any significant activity since it's a null model, but it's just a sanity check if you want. And then you can check if the actual onset increases. Having the correct onset increases it, the model fit based on the shift against the shifted predictor. So for that, again, you would use the t-test related. So you can do that and see. But that's about it. So if people have finished this, just give a thumbs up or raise a hand. And we can even skip it because we don't have anything new here in terms of the code, but you can just play around with it and see. I'll just wait for a few minutes and then
So this could just be my computer, but when I run some of these like the one sample t-test, I'm wondering if maybe it's something else, but it's taking a while to run, and I'm curious if you've run into that issue before.
it does take a little bit of time. How long, is it? It should finish within I don't know, 2-3 minutes maximum. Yeah, is that?
It just finished, so
okay.
I guess it would be a minute. Yeah.
Yeah, it does, because it needs to do 1,000 permutations and things. Yeah.
Okay.
But yeah, and these are, it's doing it on not just single values, but on topographies or TRFs, right? So it has many. Yeah, I don't know. But I found that, yeah, it does the same thing on my computer as well. Yeah.
Okay.
these are sort of should be optimized using Cython under Python. So it should be running on C code. That's sort of fast, but yeah. Okay, so I'm just going to move on. Do people want to see the answers to this, or shall I just post it later on so you can see it in your own time? There's really not much new here in the functions or the code. Should I show the answers here? Like, if anyone wants to see it, you can sort of raise your hand and I'll show it.
Okay.
Okay. So
one
yeah,
hand.
sure. Yes. So yeah, so it's basically the same
yeah.
code. Sorry.
Sorry, no, continue, and then I want to get to Justina's question.
Oh, okay. I didn't. Okay, interactive plots. Yeah, sure. I can do that after this. So yeah, so it's the same code. It's one sample test on the shuffled onset TRFs to see if there is any significant activity. And if you run that, you can see something like this. So if you remember, the color K is just the same as black. But yeah, the color, it should be black if there's anything significant. And it seems there isn't anything. If you take a look at the actual test, it will tell you that the p-value is 0.8 or something. So yeah, so it's definitely not significant since it's shifted onsets. If you take a look at the envelopes, those would be significant because you have a predictor there. That's okay. And then if you want to test if the null model versus the actual model, if you want to see the model fit increase, you can again use this t-test related, and you give it the actual model and the null model, and you want to see the increase. And if you do that and plot it, you should see that there is again an increase in some of these sensors. So that, I mean, this is a sort of almost like a toy example, but these are some of the tests that you would probably do for more complex TRF models where you have one predictor that you want to check whether that's adding that to the model is helpful or not. So any questions so far on the tutorial? That's sort of the end of the formal tutorial, and there's a few more points that I can just go over quickly, like the interactive plots. But any other thoughts, questions, anything else? Just thumbs up if people are good to move on. Okay, good. So yeah, so there are some parts of Eelbrain which I didn't go into just because of time, but there are some really interesting things in Eelbrain that are very easy. So one thing is source localization. I don't know how much people use it in EEG, but definitely in MEG, there's a lot of source localization, and Eelbrain is very easy to use source localization. It works on MNE, but it's very easy to do plotting and all of that. There are some more complex tests that you can do with Eelbrain that work on these ND variables and using these cluster type approaches. And then there's also a pipeline that's sort of in Eelbrain. You can take a look in the documentation. It's called MNE experiment in the documentation. But you basically give it like sort of like a specification file of what steps you want in your pre-processing, not actual code, but just like specifications. And then it will run that entire pre-processing loop on your entire data set, even up to computing statistical tests. So from the start of from raw data to statistical tests, you have it in one Python file, and you just run it on your entire data set. And it's very high level and very easy, but it does take some getting used to, since it's just another sort of additional syntax to get used to. But it's once you do get used to it, it's quite easy to run. So take a look at that if you really want to use Eelbrain a lot. But for simple experiments, these types of functions are good enough. And actually, most of my work I use with this. It's only for the really big ones that I try this pipeline. But yeah, then I can show a little bit about the interactive plots. So let me try that. Okay, so I'm just going to share my screen. Right, you can see my screen, yeah. Okay. Yeah, so this, So I didn't go into interactive plots a lot because sometimes interactive plots don't work on every OS. Okay, so there you go, it doesn't work. Let me try it from scratch. It's just because the way that Python is plotting stuff on different OSs and Eelbrain is doing what type of underlying GUI it's using. But if I can get it to work properly, it should be good. Let me see. Where are we? Nope.
So are you working in interactive Python shell, or is this a normal shell?
No, I just use Jupyter. It's like, I mean, interactivity is nice, but I prefer the Jupyter's cell blocks. I suppose it's only for something specific. If I really want to look into how the TRF is moving, or sometimes for ICA rejection, the Eelbrain interactive thing for ICA rejection is really nice. So for those, I may use interactive things.
Okay.
But I found that interactive plots work well on Mac, but on Windows, sometimes there are some issues. So yeah. So let me try to load some of these things. Yeah, I had this set up, but apparently it didn't work. So let me try it again. Okay. Okay, so this is sort of the interactive plot. So you can see this is normal top of butterfly. So if you take a look, there's all these hotkeys you can use to scroll and to zoom and stuff like that. So so if you want to zoom in, that's just using a hotkey and then moving it. This is probably an eye blink. So this is just the raw EEG that I'm plotting. So it's probably like an eye blink. You can move around, scale things, so on and so forth. So all the Eelbrain plots that I've been showing, you can do it interactively. So if you want to plot TRFs interactively, you can do that as well. So let's see. I'm not sure if I can get the ICA thing ready, but maybe I can. Let me try to see. Are people interested in looking at the ICA thing as well, or is this you want to do it? So if anyone wants to see the ICA, just send a thumbs up.
I guess what does it add by the interactive?
Sure. Yeah, it's just that it's basically the interactive plot. So you have all the components, and then you can basically select components on that like a GUI, and then also look at the time course of the component and the frequency spectrum of that component, and just click to reject components. So it's just easy.
Oh, okay.
Yeah, but I think it's not worth going into it because I just need to load all the ICA and the data and all of that. So it's just going to take a bit more time, and we're already almost at time. But yeah, so I think just had one more slide, which is basically what you can do next. But we already looked at this. This is basically the tutorial paper, the one that I sent in the chat. So just take a look at that and also at the code. And if you really want to use ridge regression, but you really like Python, you can do that. You can use scikit-learn that has ridge regression. And ridge regression also, we are like working on adding it to Eelbrain. So it should be there in Eelbrain too. But it's not going to be any different to MTRF. So, you can use MTRF toolbox as well. It's just if you want it with Python. But yeah, okay. So any other questions? I'm going to stop sharing and yeah.
Yeah, thanks very much for doing this tutorial.
Yeah,
it was really great.